Welcome, good morning, and good afternoon, Eaton Nation. I am Josh Kingsley, and I am back at my hosting post for today's Ask the Expert event. And today we're going to be taking your questions about the topic of harmonics. So let's meet our expert for today. Please say hello to the director of Eaton's Power Systems Experience Center, Mr. Dan Carnevale.
Hey, Josh, and welcome to everybody out there.
Yeah, welcome, Dan. Thank you for being here. And also a big thanks to Eaton Nation for coming out strong with all the pre-comments and results to the polls that we've got. That's going to really help us give you guys a great experience today. We're going to start with our normal housekeeping. To our audience, you can ask your questions via the comment sections below on both the LinkedIn and Facebook profiles. So thanks for joining us live there. And also, as an added bonus, you will be able to download a free white paper called Harmonic Solutions Explained. And it's going to provide an in-depth look at harmonics, the causes, the impact, and most importantly, as you've told us emphatically, the solutions. So we will show you how to get your free white paper at the conclusion of this. So please stick around, as always, to the end. And this Ask the Expert session is brought to you by Eaton's Power XL EGP 18 pulse variable frequency drive. Please visit eaton.com/EGP to explore the portfolio. All righty, let's get right into the questions. And our first one is going to be coming from Jacob on LinkedIn. And so I'm going to phrase this the best way that I possibly can. What are harmonics and why are they bad? Where do you start with harmonic analysis to know if you even have to worry about harmonics if you're putting in a VFD? So Dan, how would you answer that?
Josh, great way to start. And Jacob, thanks for the question. Where do you start with harmonics? First of all, what do we know about harmonics? Again, distortion on the voltage and current waveform. Where do they come from? We're going to actually take a look at where harmonics come from. So let me just draw it out here. I love to have my little drawing tablet here. What happens is that people put in motors and they decide to switch over and put in a variable frequency drive, or they put in other loads like fluorescent lighting or LED lighting or whatever, and then all of a sudden harmonics show up in their system. So where they come from is actually from the load. So let's take a look at an example with the drive. We have a motor that may be a 100 horsepower motor, and we have some harmonics that are generated by the drive, and I'll come back to that in a minute. We're going to say those harmonics come out of the drive or out of the electronic load, and they flow back up through the system. And as all currents do, currents want to flow to the path of least impedance, so they flow back up through the system and through the transformer. Now, what's really interesting about harmonics is it seems overly complicated, but it's really just Ohm's law. Voltage equals current times impedance is Ohm's law. And when we start without the drive, we have an equation that looks like this. Voltage distortion equals current distortion times harmonic impedance. And basically for the first scenario where we don't have a drive, voltage distortion equals 0 because current distortion equals 0. But as we add more and more current distortion here, in other words, let's say we go from 10 amps maybe with one drive to 100 amps with multiple drives of different frequencies, fifth harmonic. And again, we'll come back to a little bit of that. We add more and more voltage distortion. So again, we start out with a relatively clean sine wave in terms of voltage. We draw a current that doesn't look like the voltage. We call that nonlinear load. And that nonlinear load, that current doesn't look like the voltage. That current pushing back up through the system then actually causes voltage distortion. So voltage distortion comes from current distortion. The more current distortion we have, the more voltage distortion we get. And again, great question to start with because harmonic currents come from the loads. Harmonic voltage distortion ends up being part of the end result of that. And so then the next step is how do you figure out what the solutions are, and how do you model the system if you need to determine what's the best solution for it. And I'll tell you one little secret is just because you have a drive and you have some harmonics in the system doesn't always mean you have a problem. So the problems result from current distortion causing heating and things through the system, which again we can address in other questions maybe, but voltage distortion causing misoperation. So we look at this from a problem and solution standpoint, and that's really a good starting point. So Jacob, thanks for the question.
Yeah, and also a big shout to Vian and Hamid, who were part of the chat that I referenced at the beginning, who pretty much asked the same questions to help define harmonics. So let's jump to our next one, which is coming from Alex on LinkedIn. And what he's asking is fairly related, so this should follow pretty well. What are the key harmonic solutions for VFDs, and how do you decide which one to pick?
Again, that's Alex. That's a great question because if you think about it, as I mentioned, and I'll go back to I have to use the drawing tablet here. But if I put my drive on here, and I say that I have harmonics coming out of my drive, and I'm simplifying this. Obviously, it could be multiple drives, it could be multiple different harmonic loads, whatever they happen to be. But as that current comes out of the drive and it wants to go somewhere, we have to either find a new path for it to go through that's a lower impedance, going back to that voltage distortion equals current distortion times harmonic impedance, or we can actually limit that current from coming out. So what are some of the solutions? Some of the solutions I would start with DC chokes built into the drive or line reactor built into the drive, or an additional line reactor in front of the drive. And what that does is basically constricts the current. So I always think of it and think about it like water going through a hose, coming through the hose. If I constrict that hose, we've all kind of pinched a hose together, get a kind of a higher pressure out the other end, but we're really limiting the flow through there. So by putting a drive here with a line reactor or a DC choke built in, we take a current that looks something like this, and we end up having a current that looks more rounded off. And the harmonic pattern that is associated with that is much less. In other words, we have a lot less distortion. So if in the first case we didn't have a reactor, we had 20 amps of, say, fifth harmonic current. With the second case, we might have 10 amps of fifth harmonic current, and that actually is probably the least expensive version of things. So like our drives, our DG1s, for example, and our other variable frequency drives have DC chokes built right in, and 5% is kind of the right number for that. As you look at other things, we talked about if we try to take the current and make it go somewhere else, we could actually put a filter over here. So a filter looks like a reactor and a capacitor in series. And at a particular frequency, let's say this fifth harmonic current, when this current gets to this point, current wants to divide and go according to impedance. So if this was ideally 0 ohms, guess what? Current that's, even if it's 100 amps times harmonic impedance, if this is 0 ohms, then our voltage distortion goes back to 0. In reality, it's not going to be 0, but this is how harmonic currents flow through the system. And most times when you make a filter like this, half of the current or so goes this way, half goes this way. So those are kind of two things that you could do. The other thing is to select perhaps the right drive. We talked about 18 pulse clean power type drives. Our medium voltage drives, perhaps 24 pulse to keep that limit down to a reasonable level. And then you go all the way up through broadband filters in front of the drives and active front ends and so forth. So there's a lot of different solutions. And honestly, that's why we put the paper together, because it can be kind of confusing, and it all comes back to a couple things, really the technical advantages that you have and the cost. And we've put a bunch of frequently asked questions around those and made some videos around that as well. So those references are available for you as well.
So essentially, you're trying to diagnose what exactly the problem is, where it's coming from, what kind of budget you have to have for solutions, and then you're going to have a bevy of options.
Exactly. Yeah.
Perfect. Okay.
Yeah, Josh, it's like being like a power quality doctor. We use that analogy because it's, if you go to the doctor and you say, hey, doc, I have a problem, he doesn't automatically just throw a cast on your leg. He says, well, what are your symptoms? And if you look at the symptoms here, and I have a lot of heating and stuff associated with that, I know I have to deal with the current. If I have a lot of voltage distortion, I know I have to deal with the voltage. And so we kind of look at it as applying the right solution, according to what you need in your system. And sometimes doing nothing, the least expensive solution sometimes is the right solution. It just depends. So harmonics are kind of that new normal that we have to deal with.
Got it. So let's walk down that path a little bit. When a solution is correct to do nothing, kind of paint a picture of how you determine that it's not as big of a problem as you think it is.
Yeah, I'll start with another thought here. So let's say we have, again, somebody wants to convert their warehouse. They put a bunch of VFDs, and they're originally running motors on a conveyor system, and all of a sudden you put in one drive and two drives and three drives, so you convert all these motors over to have VFDs. At what point do you have a problem? There's some rules of thumb that we go by, and sometimes if you look at the kVA of this transformer, let's say 1000 kVA, if you get to the point where about 20% of your load on that transformer is harmonic type load, then maybe, you start to do some more formal analysis instead of doing just, kind of the back of the envelope kind of thing. So, 20% of the, full load of that, which is going to relate to both the voltage and current kind of issues. If you look at, this bus here, and you're looking at the voltage here, this is where harmonics are a self-infecting problem, right? So the more you put down here, the more you distort the voltage on the bus. So you go from a nice clean sine wave to something that's distorted. And as you distort the bus and you determine that I'm now having problems with some of my loads in my system, again, the one thing, Josh, about those harmonics is it's not as cut and dried as some other power issues. And, some gray areas exist, obviously. And for one situation, maybe in an industrial plant, you can live with a lot of harmonics. Maybe for a hospital with MRI machines, you can just have a little bit. So as an example.
So going back to that diagnosis, you need to know what your loads are doing and what the potential failure could be. And so a little bit of nuisance tripping every once in a while in an industrial facility might be dealt with, but an MRI tripping ever is probably a bad situation.
Yeah, exactly.
Got it. You also mentioned that those were self-infecting problems where you could be harming your own power source that you have. Is there such thing as a problem that doesn't infect yourself, but infects something else?
Well, that's actually where the IEEE standard comes in. When you think about, if you take, and I go back to a scenario where you have your transformer here and, you're feeding your loads or whatever. And then on the same system, we have, another utility customer, and you could literally be affecting those guys by your harmonics. And that's where the IEEE standard comes in at that point of common coupling, where they have to be kind of the mediators. Couple examples, Josh, that I think of when I think of that. I ran into a situation where, there was a ski lift and they had to drive on the ski lift, and as, they added more and more things to the top of this hill. More and more people were riding the ski lift. All of a sudden, the people in the really nice houses at the top of the hill with the ski lift, their lights were flickering. And so it was kind of affecting them with this ski lift. So the answer is what? Turn off the ski lift and not have people go up and down the hill, or maybe put some kind of filtering in to absorb those harmonics or send them back to the load, because current always has to flow out of the load and then back to the load, where voltage, we can deal with in other ways. Another scenario related to that was I saw somebody, this was back when people were replacing fluorescent lights a lot. They replaced like half of their fluorescent lights in a big commercial building, like 12-story building. And as they got about halfway through, those lights started to flicker. And so now you're thinking, okay, I got halfway through, all of my lights that I just put in, even though I'm saving money with them from an efficiency standpoint, they're starting to flicker. So now I have another problem. And that's where, again, you have to start to deal with it. So it could be you affecting yourself, you affecting your neighbor, or in the big scale things, like that steel mill affecting the hospital on a big scale, and the utility has to deal with it.
Yeah, and the utility is probably really interested in playing mediator in situations like a ski lift and people that are living on top of a mountain. Okay, let's get into our next question. We're going back to the LinkedIn, and we're specifically going to go to the chat that we had putting this together at the beginning. And so Brian Souter asked a question, and I'm going to try and paraphrase this as much as I possibly can. So the first things he's asking is, what's the relationship between the existence of harmonics in a three-phase system and apparent neutral currents? And so to throw a couple of the factors that he's throwing out, he's got the equipment properly grounded, and he's seeing high neutral currents at both the medium voltage switchgear and the downstream 480 VAC side, even though the plant technically does not have a 4-wire system, which would be the 3-phase plus the neutral. But he's seeing the high neutral currents coming in at his SEL 51A relays and Siemens WLS 480 volt switchgear. And the problem has been bad enough that the breakers are causing erroneous ground trip faults. So Siemens had him put in EMI filters. I know there's a ton of stuff going on there. If you can kind of help unpack what we can do to talk about this, and maybe comment on the Siemens proposed solution and what your thoughts are on that.
Okay. Yeah, there's a lot in there. And Brian, what I'll do is now that I'm looking at that question, I'll reach out to you after this and give you more specifics, but I'm going to kind of address your question the best I can, just to kind of give you a little bit of an overview of some of the stuff. So if we look at, a three-phase system, and we have, you know, three phases going out and a neutral. What you were referencing was, you know, if I have loads on each phase connected to neutral, you were talking about zero sequence a little bit, like those, you know, if we have, let's say phase A, 10 amps on phase B, 10 amps on phase C, if that's 60 hertz current, because it's all displaced by 120 degrees, we have 10 amps plus 10 amps plus 10 amps. In the neutral here, we get zero. But what's interesting is you mentioned zero sequence. So if I have, let's say 5 amps or, you know, 10 amps or whatever of third harmonic or zero sequence, that current is actually additive on the neutral. And so when it gets back to this point, it's 1, 2, 3, and it adds up to be 15 amps in this case. That's why people historically have doubled neutrals and stuff like that. Now, when you look at how things go, what you're referencing is you're talking about a medium voltage system and a 480 volt system that doesn't have a neutral. So in this case, we're not talking about those type of low frequency, in this case, third harmonic, for example, zero sequence harmonics. What you're talking about, I think, is some of the higher frequency harmonics. And those can come from sometimes the outputs of VFDs, the pulse width modulated output. And we usually don't think about harmonics from coming from the output of the drive. The drive is a rectifier, DC bus with a capacitor, and a inverter. And the pulse width modulation on this output, that high frequency stuff, sometimes I've seen, you know, if the input current looks like that double hump current that I drew earlier, the output current can have some 39th harmonic, like really high order third harmonic. So again, I'll get back to you on some of the details of that, but where I've seen this in larger industrials is the influence of those currents coming through, not the conductors themselves, because there are no conductors in your situation, but the capacitance to ground. They can follow that capacitive path, especially the higher frequencies. And that's why the EMI filter was recommended likely. And if it took care of the problem, that would make sense, because you're actually putting a conductor in parallel with that capacitance to ground. So much, you know, very complicated kind of situation, but I'll definitely reach out to you and talk through the details of the answers to that. Oh, by the way, before I forget, sorry, Josh, one of the things that does affect on 480 volt system is this high resistance grounded systems. You can see that on the voltage measurement on the HRG system. If you measure current, a lot of times you can filter that out or not see that and just look at the 60 hertz part. But if you're looking at voltage to ground, sometimes you will see that pick up.
Got it. Thank you, Dan. And hopefully that gets us down the path to a right question, Brian. Do us all a favor and check your email. Our Eaton Electrical Services and Systems team is going to be reaching out to you to discuss this further. They'll be able to set up a time. So, I mean, this is the Ask the Expert session, and we truly have an expert on here with Dan, but we also have experts outside that can help, and that's what they're there for. So be looking for a note from them. All right, the questions are coming in fast and furious, but the producers are in my ear as normal, reminding me to tell you that this episode of Ask the Expert is brought to you by the Power XL EGP 18 Pulse VFD. Visit eaton.com/EGP to learn more about the product. And Dan, let's jump back into the questions. And it looks like this one's coming in. We're going to jump over to Facebook, give some love to them. And this one's coming from Ardeth. And this looks like a good one as well. And we've touched on this a little bit, but can we get a little more specific into, is there a way to select a VFD so you can avoid harmonic problems?
Yeah, hey, Ardeth, that's a really good question. Whether it's a drive or really any electronic load, let's say, you know, again, LED lights or whatever, we say that those electronic loads have characteristic harmonics. So I've been drawing this current that looks like this, and I'm going to back up a little bit and explain that a little bit more. This current has a 60 hertz component, and it has other frequencies that added together kind of a superposition add up to be that waveform. And so like it might have a fifth harmonic and it might have a seventh harmonic. And you say, well, how do you know which frequencies those are? So fifth harmonic is 5 times 60 or 300 hertz. How do you know what that waveform would have? There's a kind of a nice, easy calculation here. It's NP plus or minus 1. So when we have 6 pulse drives, that's 6, N is just an integer, 1, 2, 3, 4, 5. And then so it's 1 times 6 plus or minus 1, which would give us 5th and 7th, and then 2 times 6 plus or minus 1, which gives us 11th and 13th, and 3 times, so 17th and 19th. So if I were to take that same equation and say, now I have an 18 pulse drive, so what would be my predominant harmonic I would have? It would almost look like I have a nice clean sine wave, and I would actually have 18 plus or minus 1, 17th and 19th, and then 2 times 18 plus or minus 1, so 35th. You're stretching my math here, Josh, and or 35th and 37th. But anyway, when I do all that, and I look at the frequency spectrum, so if this is magnitude, and we'll call the fundamental 100%, so the fundamental being 60 hertz, I would have 5th and 7th and 11th and 13th and 17th and 19th. What you notice is those frequencies, as they go up in frequency, the magnitude of the harmonic goes down. So this is 5th, 7th, 11th, 13th, 17th, 19th, and so forth. Now, when I draw the spectrum for just the 18 pulse drive, I still have my fundamental. By the way, what's the fundamental doing? That's what's doing the work. The harmonics are kind of extra currents that are part of the process of converting from AC to DC, and we have to live with them. So if you have less harmonics to start with, 17th and 19th, all these other ones go away. That's why, we look at certain applications and we say, at some point, I might want to go with an 18 pulse drive because, even though it might cost a little bit more out of the gate, I might not have to deal with the harmonics after the fact. So we look at, where can I take advantage of, higher pulse numbers and so forth. And I can do that within the individual drive itself, and or using phase shifting transformers as an example.
Got it. And hopefully that helps, Ardath. But Dan, I want to kind of dig into something a little bit more. So if you pick the right drive and equipment and gear right out of the gate, you can actually use less corrective equipment later. So we're really digging into the question of, is this a retrofit or is this a new build? Can you kind of expand a little bit more about if you would diagnose the situation differently one way or the other, and what your approach for each of those would be?
Yeah, that actually, Josh, that's a good follow-up, because what I find is, like, a lot of times designers will come to me and say, hey, am I going to have a problem with this? And this goes back to those kind of, I have 20% more of my, transformer capacity. Am I going to have problems? I mean, there's no guarantees with harmonics in terms of magnitudes and certain systems. You really have to look at it from a system level. But yeah, so when you start to think about the solutions, if you pick the right drive out of the gate, you could end up having less, filtering and so forth later. So one of the things that we addressed in the paper was kind of around the whole, individual drive approach versus system approach. And so that really does kind of go into those kind of things. And again, it's a technical and economic choice. I'll show you an example here. So if I have my source and my transformer, and again, I'm running this as a simplified case, but if I have a bunch of drives here and I'm creating some harmonic distortion, and I start to, mess up my voltage distortion here, and maybe I want to transfer over to a generator. What we've seen in the past is, you have a generator here, and when you're running on the normal source, this utility source is, transformer is 5.75% or, something like that. Generator impedance coming back, looking into that, is 18%. So as I look at, what am I going to do to take care of the harmonic issue? Well, maybe when I'm running on my normal source, it looks like that. But when I'm running on my generator source, my voltage distortion really gets kind of crazy. And the reason is because, remember, going back to Ohm's law, voltage distortion equals current distortion times harmonic impedance. And if the harmonic impedance here is 3 times on the generator as it is on the transformer, guess what? If I put a single solution in here, then all the harmonic current goes here no matter which source I'm on. So sometimes the answer is corrected on the, on the system level. And again, this is drawn as one drive, but this could very well be 10 MCCs full of drives. So looking at it from that standpoint, the other thing is, let's say I did have I didn't want to have to deal with this after the fact. If I make this 18 pulse, 90% of the time, I don't have to think about it anymore. Sometimes we do passive filters. Sometimes we do active filters. Active filters actually look at the current going through the system. And an active filter is like your cell phone has noise cancellation. Basically, it injects equal and opposite frequencies. So if the harmonic's coming out of the driver going this way, the active filter sends them that way. And again, since current flows in a loop, it goes out and back. And you know, as far as the bus goes, the voltage goes back to normal. So yeah, lots of different things to think about related to that, but it can be an individual drive solution or a system solution. And let me just add one more thing to that. Let's say this is a water treatment plant. Let's say you had 10 drives across here. Okay, so I'm going to start actually over here. Let's say you have your source and you have 10 drives. Well, one of the things you could do is you could put a filter on every single drive, okay? And I won't draw them all out, but if you end up with a filter on every drive, you know, so you have a drive plus a harmonic filter, that adds a little bit of cost to every drive, but it might be the right way to do it. Now, what if you had 5 drives that are running all the time and 5 redundant ones? Well, you basically have 5 filters that are sitting there with nothing to do half the time. So now that might be where a system level, like an active filter. So even if an active filter costs more to begin with, you might actually put it on a system level and still be able to deal with the problems on many drives instead of one drive. I don't know if Josh, if that helps to kind of clarify it a little bit better.
So the real question is, do you want to put the active filter in, put the extra cost up front, or do you want to do it in service calls and you're adding an active filter to somewhere between 5 and 10 drives if you've got redundant in that particular situation?
Yeah.
So let me ask one more quick follow-up to you. You mentioned having a main power source and a generator power source. So let's think of a scenario where you decide sometime down the road after the building was built originally that you need to have a backup generator. What are the things that you're thinking about? I mean, it seems like you mentioned that the impedance could be different based on the main power source versus the generator. So kind of talk about how you would diagnose that up front as you're doing the generator retrofit.
Yeah, and what I run into a lot, actually, Josh, is if you have, you know, if you do have your generator connected in here, and again, this would be some sort of transfer scheme. So I'll just draw it as if they're both connected in parallel, but you'd have a generator here. Again, this is, let's say, just simplified 6%, 18%. And then you have a transfer scheme with breakers or contactors or whatever. And then, you know, you feed your loads down here. So if you had no generator, but you added one later and you had a whole bunch of harmonic producing loads. And again, we're going to call harmonic producing loads kind of the new normal, anything electronic, but specific to today, we're talking about drives. But you have all these VFDs or other things that are adding harmonics to the system, and they want to flow back to the path of least impedance. If the generator is offline, that current's going to flow back up to the source. And by the way, it's going to flow out, say, for example, on A and then back on B and C. A lot of people think harmonics flow to ground, but they don't. They flow out on the phase conductors and back on the other phases or the neutral. But anyway, so as we send the currents out, and then we switch over to the generator. So we take this out and we run over here to the generator. Sometimes we'll have problems. And like I said, maybe we go from a voltage distortion that looks somewhat bad, you know, to something that looks horrible. And when I say horrible, I mean, it could get really ugly pretty fast. Because again, you got 3 times the impedance. And what's that going to cause? You might actually have what we call multiple zero crossings. I'll explain a couple of scenarios with that, but you could have a bad voltage distortion. So by cleaning up the harmonics here, this goes back to normal. And what's really interesting, Josh, you kind of made me think of something. What do people usually test a generator with? They'll bring in a resistive load bank and they'll test it with a resistor. Well, of course, if you have a linear voltage and you have a linear current, you have no distortion. It's going to look fine. And then they have a real scenario where the power goes out and they're running on the generator and they have a problem. So this is something that I have run into a lot and people need to deal with. What I mentioned over here with multiple zero crossings is I had an example where somebody was using a welding line and in an auto plant, and they were, you know, running the stamping presses were causing enough voltage distortion on the system to cause the welder, instead of being, you know, 20 cycles long, the weld was 8 cycles. They were counting. A nice way to keep track of time, by the way, is if you're looking at a sine wave, every time it crosses 0 here and then, you know, back here again, that happens to be 16.67 milliseconds. Well, if it crossed there and here and maybe over here again, now every time it crosses zero, it thinks that's 16.67 milliseconds. So the welding line that was supposed to be 20 times that was only getting 8 times that. They were having bad welds and stuff. So again, harmonic problems are a little bit difficult to track down after you have this issue, because it's not always just like something overheats and burns up. It's something over time heats and burns up, or this misoperation thing is a little bit intermittent. Like sometimes it does it, sometimes it doesn't. So again, the things with the generators, and especially with voltage distortion that gets pretty bad, can be difficult to track down, but also, it again follows that simple rule of electricity, which is Ohm's law.
Yeah, in your weld situation that you bring up, there's a strong possibility that you don't find out you had a bad weld until a little ways down the path, when whatever you were welding was actually installed, and the customer's coming back to you saying, what are you doing?
Well, there's actually a recall on an actual part on a car. I won't tell you specifics, but yeah, because of that. And so, yeah, that's one of those things. You're exactly right. You wouldn't know it. We call that product quality as a result of power quality, right? So that can happen in a lot of different scenarios.
Got it. Okay, so I'm going to jump into another Facebook question here. And this one's from Preston, and it says, we have a facility with drives on almost everything. The incoming transformer is a 2500 kVA Y. It says YY. I'm thinking they're meaning a Y delta. But it's 7.2/12.47 kV to 277/480. Lots of harmonics on utility, but they disappear when transferred to the generator. So, I mean, it sounds like a pretty similar scenario to what we were talking about using generators. So let me know if you caught everything that I said.
I think so. So 1247, 2500 kVA, lots of harmonics. Everything on here is on drives. So they're running everything, and he says they disappear. The harmonics disappear when they go on generator. I don't know if he means specifically, and maybe you could have a follow-up question, but so the current, again, has to flow somewhere. So the current's going to typically flow out and back on the transformer out to all the different drives. So if we transfer to the generator, we would have the same thing. If the generator is running in parallel, likely a lot of the harmonics will still go back to the utility, as that's a lower impedance in terms of current. Now, as far as voltage goes, what he may be saying is it runs a lot better on the generator. The opposite could be true in terms of impedance. Remember, we said this is Z is 5.75. If for some reason he had a very large generator here, it's a comparable thing. So if this was, let's just exaggerate it, say 10 MVA, 10 MVA would be 4 times bigger than that. So even though the impedance is bigger in terms of 18%, the effective impedance would be 2,500 divided by 10,000 times 18. So you end up with something that's going to be closer, or actually less than the original impedance. So I'll follow up with you. Did you say Preston? So Josh, I think I can follow up with the specifics around that question, or if he wants to follow up with an answer. But generally, harmonic currents have to flow. That's just a natural thing of the system. Now, the other thing that could happen is, let's say this generator is very small. The current from this is actually an interesting phenomenon that happens. The current from the system could look like this when you look at the harmonics on the drives. And then when it's run on the generator, if it has really, really high impedance, it actually could look like this. And so he may actually be squashing out his harmonics by having such a high impedance here, that this looks like a line reactor in front of all the drives. So lots of things. It's a very dynamic situation, can go on. But that would be, a couple guesses, and then I can follow back up with Preston.
Yep. Diagnose. And don't forget the Eaton Electrical Services and Systems team is also available to help talk through some of this. And keep in mind, we have the white paper coming as well.
And Josh, that's a really good point. So one of the things you do want to do, it sounds like he's been taking some measurements. So measurements are really the key. So diagnosing that with measurements is really important.
Got it.
I'm sorry, I keep interrupting you, but it goes back to the question you asked me earlier, which is how do you know new system versus old system? I think I forgot to answer that part of it, which is on a new system, you have to model. On an old system, you can measure. And that's really, it's a lot easier on an existing system to figure out what's going on versus on a new system, but you can do it on both.
Got it. And did have a follow up. It is YY.
Uh,
And so it looks like he answered most of those questions. And if he does come back with anything else, you can pop that up to the top as well. Next one I'm going to go to is LinkedIn. And this is Ibrahima on LinkedIn. And his question is, what is the impact of the other harmonic into the system? And so an example is the first, second, and third harmonic. You were talking about being tested on the mass. So let's go back to that again.
okay. So let's do this. Ibrahim. So this is okay. If we look at the fundamental 60 hertz, then we look at, let's say, the second harmonic, which is going to be, twice as fast. And then we look at the third harmonic, which, all those. What we can do is there's actually, I don't know if anybody's done, this is a power systems thing, but there's a thing called sequence, positive, negative, and zero sequence. So positive sequence is what we think about for 60 hertz. So positive sequence is, A followed by B followed by C. They're 120 degrees apart. They rotate this way, and they kind of form, so phase A is there, phase B is here, and then phase C is actually here. And so those three phases added up, again, we say would add up to zero, but that's a three-phase system, positive sequence. There's a neat kind of thing that happens when you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll just go there. It goes positive, negative, zero, positive, negative, zero, positive, negative, zero, positive, etc. Okay. Positive sequence harmonics, which this one, this one, this one, this one, they act like the 60 hertz stuff. Negative sequence harmonics are kind of like A, B, C. We talk about, let's say for a motor, we have a motor that spins, and the 60 hertz is making it spin this way. The negative sequence harmonics kind of make the motor want to spin the opposite way. So when you have a lot of, let's say you have a system, and I have, enough voltage distortion on my bus here, even across the line motor might see, a voltage that looks like that, which means it's going to draw a current into it that might be, say, for example, negative harmonic, like, which is the fifth harmonic. So I'm creating, maybe with some VFDs over here, harmonic currents that are going out, and I'm screwing up my bus voltage. And then that negative sequence harmonic current comes into this motor, makes it want to spin backwards. It's kind of like driving with your foot all the way to the floor in the gas pedal and kind of like tapping your brakes a little bit. It's very inefficient. So the forward motion doesn't allow the motor to spin as fast as it would want, and it makes it less efficient, heats it up. You can have premature damage and failure of motors. So that's negative sequence harmonics work like that. Zero sequence harmonics we kind of addressed earlier, and they add up in the neutrals. And so now you can have overheating in the neutrals to the point where you can have double the current in the neutral as you do on the phases. So going back to our earlier example, phase A, B, C, neutral, I could have 10 amps of, say, 60 hertz, 10 amps, we'll go with 10 amps of each in this case. 10 amps, 10 amps, 10 amps, 10 amps, 60 and 10 amps of, let's say, third harmonic, or any of the zero sequence. And usually we talk about the odd multiples of the third. So third, ninth, sixth isn't usually very common. But anyway, what we would have is on the neutral out here, we would have 0 amps of 60 hertz. As we mentioned before, 60 hertz A, B, C adds up to 0. But the third harmonics, A, B, C, 10 plus 10 plus 10 is going to add up to 30 amps on the neutral. Now, if you look at what this phase wire is going to be rated here, it's going to have 10 amps plus 10 amps, but you do that in an RMS fashion. So it's 10 squared plus 10 squared, and that's going to be 14.1 amps. That's square root of 2, by the way. So 10 squared plus 10 squared, it's 14 amps on phase A. That could be a 20 amp wire, 12 gauge wire. If I use 12 gauge wire in my neutral, it's only rated for 20 amps. I have 30 amps, so I'm going to burn up my neutrals. That's why they double the neutrals. So zero sequence harmonics add up on the neutrals. And we talked about it earlier with the question about the media voltage and 480 volt systems, where maybe high frequency ones. I mentioned 39th harmonic. So if you keep expanding this list out, you get to 39th, it's going to be 0 sequence. Positive sequence harmonics just add extra current to the system. It's like adding extra load on your wires, and it can kind of overheat things. Negative sequence kind of tends to make things want to go backwards. 0 sequence tends to add up again in a way. And by the way, these also rotate as vectors or phasors, but they rotate together. So when you add them up on the neutral, all three of them add up exactly in phase with each other, if I could draw it correctly. And so what you end up with is 3 times the current in the neutral. So that whole discussion really goes to the fact that like each of the harmonics or characteristic harmonics have sort of different patterns to them. And if you look at VFDs, we say 6 pulse, we already said 5th, 7th, 11th, 13th, 8, 12 pulse, we could figure that out, 18 pulse, we could figure that out. But like fluorescent lights or LEDs or maybe a 3-phase rectifier, for vehicle charging, for example, that might have 5th, 7th, whatever. This might have 3rd, 5th, 3rd, 5th, 7th. LEDs might have 3rd, 5th, 7th, but they might be a different spectrum, a different pattern. The nice thing about harmonics is they're pretty predictable in terms of the characteristic harmonics, meaning the signature associated with each type of harmonic. So hope that helps answer the question a little bit.
Got it. Next question I'm going to jump to. This is on LinkedIn, and this one comes from Ray. I know that you mentioned the regulation earlier, but let's talk IEEE 519. So maybe just get into what is it, how do you use it, and why does it matter?
Did you say Ray, Josh? Yeah. So
correct, Ray.
Ray, that's a great question. And 519 is an important, topic around harmonics. When we think about the voltage and current distortion that either our loads create or our neighbors' loads create, the current distortion is going to cause heating and other things in our system. So we kind of have to think about that and how we're going to affect ourselves. If that current goes back out onto the power system, it may actually affect our neighbors a little bit through the transformers that we use in common with the utility. But if we screw up the voltage at the utility level, now we have to deal with that. It's going to be more complicated. And so again, the utility is the mediator, we'll call them. And we say that point where everything comes together is the point of common coupling, the point where one customer shares the source from the utility with another customer. And the 519 standard actually is, it's interesting. I have it, you can kind of look it up, but it's about a 20-page document. And, when it first came out in 1982, roughly, they added a whole bunch of information into it. And they for a long time, for about 10 years, they worked on reviving it, redesigning it a little bit. And in 1992, they redid it again. And it's one of those things that you think should be updated pretty frequently, but it wasn't updated for a long time until 2014 was the last revision. And that's the one we're using today. But they went from about a 100-page document down to about 20 pages. And they try to be very prescriptive in terms of what they're doing with that. So if you have, again, a single utility source and let's say multiple customers or multiple transformers that are fed off the same source, sometimes you end up with basically what would be the harmonics coming from one customer affecting, let's say in a VFD scenario, something like that, affecting another.
Real quick, can we pull up his drawing on the screen as well? Yeah, sorry. Go on.
Yes. So as these harmonics come out of this system here, again, and there's always transformers back through the system. So if this current is affecting this transformer, it might actually cause damage to that, and this customer could see it. So this is customer 1 and customer 2. So there's tables in the IEEE 519 standard that basically define the current distortion that you're allowed to push up through your system and the voltage distortion that you're allowed to create at the common point, at the point of common coupling. So sometimes it's on the primary of the transformer, sometimes it's on the secondary, depends. But when you think about it, it's all related more to voltage than current. And people say, well, why would you say that? And it really becomes this. They use this term, we use a term called ITHD. What's ITHD? It's total harmonic distortion. That's the sum of all the harmonics, second squared plus third squared plus, I4 squared, dot, 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 whatever, divided by the fundamental, the 60 hertz. That's THD, total harmonic distortion. And any given time, you can calculate that. With the IEEE 519 standard, they changed that to ITDD, total demand distortion. And what that means is everything on the top is relatively the same, except you're using kind of a worst case scenario demand. And then this is the demand situation when you're at your peak. So you might have really light distortion, or let's say in terms of amps overnight, but the THD could be very high, but your TDD is what's important. So how badly are you screwing up the current on the system according to the size of the system? And remember the 20% reference I gave earlier? Let's say your load on your transformer or this transformer is 50% of its capacity. So they're going to let you produce less. So the ITDD limit is based on your short circuit KVA. So the short circuit amps, I guess, and it's based on your load. And the ratio of those two determines how much of a level they'll allow you to. And most of the time, it's between 5% and 20% distortion. So when you look at TDD values in the IEEE standard, that really says I can't screw it up more than 5 to 20% in that range. Now, if you look at an 18 pulse drive, most of the time you're going to be below that 5%. So that's where, going back, Josh, to the original question that we talked about, you don't even have to deal with it at that point because it already kind of quote unquote complies with that. But when people say comply, that's a little bit of a interesting thing, because we're not really, the way that the standard is written is you only comply at the point of common coupling. So people sometimes use it down into the system, and we could talk about that more if you want. But the voltage distortion levels, the part that it's really referring to more importantly is VTHD here. Usually, that goes by voltage level. So if I'm at 480, for example, that's the one change that was made from 1992 to 2014, and it went from 5% THD to 8% THD. And what they found was you didn't have to be quite as clean on most power systems at 480, so you could allow a little bit more voltage distortion. But again, there's no magic number. So as soon as you get to 8.2% distortion, everything is going to start failing. But those are guidelines, and the key word there is kind of recommended practice. So I don't see the utilities kind of like going out and jumping on people and saying, hey, you have to do this proactively. But when there is a problem like the ski lift we gave earlier, they can be a little bit more proactive about it, trying to fix those problems. So does that kind of?
Yeah, I think that definitely gets into the IEEE thing that I noticed more than anything is I always kind of had the impression that regulations like that changed on a very frequent basis. So it's kind of nice to know that there's been a level of consistency, and they've also tried to bring clarity by making the actual publication a little bit shorter. So I'm going to get into two questions here that I think we can have you relate, just to make sure that we hit as many as possible. So Ashish from LinkedIn asks, what's an active filter and how can we address these harmonics in real time? And then Vinay on LinkedIn also asks, what are the losses that occur in a filter? So I think we're talking filtration.
Okay. I'm going to start over here with my drawing. And what I'll do is, let's talk about an active filter again first. So let's say you have, and I'm just going to draw it now as simplified form, is just a constant current source. So no matter what your harmonic source is out here, we're going to say there's a certain amount of harmonics coming out of there. And that could be a combination of things. It could be, let's say it's a 6 pulse drive. So maybe I have 100 amps of 5th harmonic current. I could have 30 amps of 7th harmonic current, and I could have 10 amps of 11th harmonic current, and I can have 5 amps as an example of 13th harmonic current. Okay, current, as we mentioned, is going to flow out and flow back. And one of the things that I think is very important to understand is current has to flow in a loop. So no matter what, it's going to flow in a loop. So if current is created, meaning we allow that drive or that load to create the current, it's going to flow in the loop and come back. So where does current want to flow? It wants to flow the path of least impedance. And in this case, it only has one path. So it flows out on phase A, back on B and C, for example. if I put a standard harmonic filter in, I mentioned this earlier, and I kind of glossed over a little bit, but basically what you do is you tune this filter. And if you look at a frequency spectrum of that, you look at basically something that looks like this. If this is impedance and this is frequency, you have a point where that filter looks almost like very, very close to zero. Now it's not really zero because there's a little bit of resistance in here. So let's address that in terms of losses. If I push current through that path, first of all, only the current that's kind of around this frequency here wants to flow through that path, because as you look at the impedance quickly is high here and high here. So the fifth harmonic filter, fifth harmonic is here, seventh is here, say 11th is here. You're going to get, a decent amount of fifth through it. So maybe instead of 100 amps going there, maybe you have 50 amps here and 50 amps there. And then you would determine the losses in that, which is going to be minimal because that resistance is fairly small. But you're not going to get rid of much of the 7th, much of the 11th or the 13th. So they're going to want to still flow back in the system. The benefit, though, is the 5th is the biggest one. So we can get rid of that in a fairly simple way. But this takes a little bit more design, and you have to make sure that it's not going to be overloaded in the future. And honestly, the main benefit of harmonic filter, believe it or not, is not harmonic filtering, power factor correction. So you size it usually for power factor, and then you get the benefit of harmonics. So we could talk about that more, but this is really kind of the key. Now, if I don't have this kind of filter, and let's just take this out for a second, I put an active harmonic filter in here. Active filter. Okay, now what does an active filter do? An active filter senses what's the current coming through the system, and a lot of times it'll sense it here with CTs on that main incoming line. And then what it'll do is it'll inject equal and opposite currents this way. So if currents flowing this way and this way, say out on phase A, back on B and C, out on phase A, back on B and C. Where these two meet, again, it's like noise cancellation in my earphones here or in your cell phone. It basically cancels it out. So this fifth harmonic here, if it's 100 amps going this way, it literally could put 100 amps going this way and cancel it out. And so what you see back here then is 0 amps. And the really nice thing about that is you could do that at multiple different frequencies. So essentially you could get it for all these frequencies. And again, if you think about like the benefit of that, it's huge. But as we talk about in the paper, this is also the most expensive solution. So you think about, if I had, remember going back to the example where we had 10 drives and 5 of them had filled, 5 of them were running all the time and 5 of them weren't. You don't know which 5 are going to run. So maybe an active filter is still cheaper than putting a single filter or multiple filters on the system. But does that, so that kind of gives sort of an overview of how active filters work. But the other part of that, addressing losses, are what does this thing do? It injects current, and the way it injects current is through a power converter, and this thing has losses. So let's say you measure, not current up here, but let's say you measure power, kilowatts. And let's say your load was, 150 kilowatts. And you have all your harmonic current on there, and you turn off your active filter at 150 kilowatts, and then you turn on your active filter. Your kilowatts actually will go up a little bit. And the reason they go up a little bit is because the current that you're taking out of here is not really real power, like kilowatts. It's similar to reactive power in the sense that it's distortion power. And what it turns out to be is as that current's going through the system and getting corrected by this one, this actually might have, let's say, 2 to 5 kilowatts of losses. So my power that I measure on my system with that active filter on is 150, say 155 kilowatts with that on. So, your current originally looked like this in terms of very distorted. And what you're going to end up with is a really nice, clean sine wave and power factor corrected and everything. But you're going to pay for it with a little bit of losses. So get rid of harmonics, add a little bit of losses, but the benefit is there. And again, it's sort of a system level thing, which is what kind of one of the things we address in the paper.
Got it. Okay. Next question that I want to ask, this one comes from Bob on LinkedIn, and the question is regarding high order harmonics. Do you see any specific high order harmonics that tend to be more damaging than others?
I mean, that one is one of those things that's kind of system specific. I think going back to the earlier question that we talked about, because of capacitance. So all power systems have inductance and capacitance. So when you do have higher order harmonics, depending on those capacitive paths, think about the impedance of a capacitor. And when I say capacitive paths, I'm talking through air, power conductors that have capacitance to ground or capacitance to other cables. When you think about a capacitor, it's 1/2 pi times the frequency times the capacitance. And so if you have a fixed capacitance, as the frequency goes up, the impedance of that path goes down. So what's going to happen is high frequency currents can follow those paths. Now, if it's zero sequence, those are the ones that tend to find those ground paths that we talked about earlier. And, so 39th or 45th or whatever the odd multiples of the thirds way up there. But as you look at, like, let's say 17th and 19th harmonic, usually those magnitudes are so small that they're not really as effective on, causing damage or problems with equipment on the system as nearly as much as the low order harmonics like 5th, 7th, and 11th and 13th or third harmonic on single phase systems.
All right. It looks like we have one more question. We got time for one more question. So I'm going to ask one that I think is going to be fairly quick. This is Dora Mani from LinkedIn. And the question is, what's the difference between THD and TDD?
Okay. I'll draw this out on a different sheet here. So we go and again, the TDD really gets addressed in the 519 standard. So THD is going to be like all of your harmonics squared divided by the fundamental. So, and again, you can do this for voltage or current, but most of the time in this case, for TDD, we're only talking about current. So let's say we're going to use an example where we have fundamental 100 amps, third harmonic 30 amps, fifth harmonic, say 12 amps, seventh harmonic would be, say, 4 amps, and 11th harmonic will be 2 amps or whatever. So this is fundamental, third, fifth, seventh, say 11th. Okay. So the fundamental here is 100 amps. If I take 30 squared, so I get 900, and I take plus 12 squared, I get 144. I take 4 squared, 16, and I take 2 squared, I get 4. What you'll notice right away is when you square these terms, the biggest ones really become the predominant ones. So I don't have my calculator handy, but if I calculate this out, I would guess that you're going to get somewhere in the 30s, say like, I don't know, 33, say, amps. I'm just going to guess. It's not really that relevant for the exact numbers here, but I'm going to say, once you take this, add it together, and you take the square root, say you get 33. 33 divided by 100. So we multiply that by 100%, and we get 33% THD, okay? Now, remember earlier I mentioned if you were running overnight and you had like a light load condition, you might have a higher percent THD. What can happen is, let's say the fundamental overnight goes to 50 amps, but mostly the rest of it stays the same. So THD, you could have, 33 divided by 50. And now guess what my THD is? 66%. And so you would say, is this number worse than this number? And this is where THD can get you in trouble. It's really the same. The same amount of harmonic current is flowing through my power system and heating up my equipment and whatever in actual amps. And actual amps are the most important part. Okay. So what TDD tries to attempt is to try to make sure that you're using the maximum demand number so that you're not artificially giving a THD that's way high. And so, so most of the time, let's say your maximum demand was 200 amps. So now your actual THD would be, 33 divided by 200, and that could be roughly, 16.5% demand, so, or TDD. And so going through all that, and what I mentioned earlier was the 519 standard says I could never go above 20%. This number would be within the 20%, and we would have to carefully look at that, see if it makes sense. This number's above, this number's above. But honestly, they're all the same amount of harmonic current. So sorry,
Dan, I hate to do this, but we are at a point where we really do need to keep this going. We are at the end of our time. We are going to keep answering questions. So anybody that didn't get their question answered, we will be following up. But what I want to do right now is pause and show on a screen a QR code. So what I need everybody to do is open the camera on your phone or your smart device, your tablet, whatever it is that you have in your hands. Point the camera to the code that's on your screen, and you're going to see something pop up that's going to take you to a link. It'll ask you if you want to accept that. Please do. And it'll take you to the spot where you can download the application notes that we talked about earlier. And so we're going to leave this up for just a moment. So, please, again, scan the QR code and it'll take you to get that. And we will post this code on the event page at the end of the broadcast. So please make sure that you go to that. And to learn more about harmonics and how to address the issue, visit eaton.com/harmonics. And that's eaton.com/harmonics. And I do want to thank not only Eaton Nation for showing up with all these great questions, but also I want to thank Dan for joining me today. And just invite everybody to come back next month, for our next Ask the Expert Live. And everybody have a good day.
I really appreciate it. All the work you did. Thanks.